Hello, everyone. So it's a pleasure to welcome you to this next event of the 40 Under 40 lecture series. Today, it is my pleasure to introduce Carmela Russo is a researcher at the Italian National Research Council, the CNR, and at the Institute of Science and Technology for Sustainable Energy and Mobility, STEMS, in Naples. The research interests of Carmela are mainly focused on synthesis and characterization of carbon materials produced in high temperature environments, which are of environmental and practical relevance. She obtained her PhD in chemical engineering at the University of Naples, Federico II, in 2013. From 2014 to 2016, she worked as a postdoctoral fellow at the STEMS laboratories of CNR, where now she's a permanent researcher and she's developing analytical and spectroscopic methods for the characterization of carbon from different sources as soot, pitches, chars, and so on. For her research work, she has been awarded the Bernard Lewis Fellowship from the Combustion Institute. This was in 2014. And in 2015, she also received the prize called Ricercatamente as one of the best young researchers of CNR. She has a large number of peer-reviewed papers in leading journals. I invite you now to enjoy her presentation. And she will talk about probing soot nanostructures and composition by spectroscopic diagnostics. Thank you very much for having accepted our invitation, and I give you the floor.
Thank you very much, Alessandro, for your kind presentation. And I would like also to thank the Belgian Section for organizing this lecture series. I think this is a very nice way to celebrate your anniversary. And I'm about to present the results obtained in the last 10 years about the investigation of soot nanostructure and composition by spectroscopic tools. Here, the outline of my presentation. In the introduction, I will give you the framework on doing research on soot nowadays. Then I will describe in detail the method developed for soot characterization and based on Raman, infrared, and UV visible spectroscopy. And in the last slide, I will give you a short overview on our most recent results obtained from the methods described. Someone of you may ask why we are still here talking about soot. I mean, it's a very question everywhere, from a newspaper to politics to scientific conference. We are talking about green energy transition, so the need to use renewable energies and need to decarbonize the energy sector. So soot seems an unfashionable topic. However, he is still a topic of research. And I think that there are several reasons to still study soot, and in the next slide, I will show you some of them. First of all, soot can be viewed as a pollutant. The share of fossil fuel in total primary energy supply is still around 80%. And this percentage will not change too much, especially in the transport sector, even in the most visionary of the scenario. This is due to the fact that there are problems related to energy density and recharging time for aviation and maritime transport, and also for heavy-duty vehicles. On the other side, for medium and light-duty vehicles, there are problems related to critical raw material supply for electric vehicles, and also to the still slow development of infrastructure and technologies for free carbon fuels. If we cannot decarbonize in the short term the transport sector, for sure we can defossilize it thanks to the use of sustainable fuels. Sustainable fuels are alternative fuels derived from biomass and waste, as agriculture residue or municipal solid waste. And to this regard, it has to remind that European Union has set a share of renewable, sustainable fuel in jet fuel of 70% by 2050. However, this diversification of the sources for sustainable fuel production will imply a very complex molecular composition of the fuels and also the not negligible presence of other kinds of atoms like nitrogen and oxygen. This may lead to unaware effect on particulate matter emission. It has been already found that substituting ethanol, gasoline with ethanol in a GDI engine leads to the formation of smaller particles. And so there is the need of a systematic investigation of particulate matter emission from this sustainable fuel before they arrive to the market, because it has to be investigated, particulate matter emission, not only in terms of size and number, but also in terms of composition, because it has been found that this is a tricky aspect for oxygenated fuels. Another reason is again regarding soot as a pollutant. It has been reported that the main sources of emission from road transport are due to tire and brake wear. And regulation on this kind of emission are coming soon. And also, hydrogen fuel engine can be a source of particulate matter emission due to the lubricating oil thermal decomposition. So there is a need to understand the formation of particulate matter from these unconventional sources, and also to find the formulation of tire, brake, and lubricating oil to minimize this emission. The further reason regards soot as a nanomaterial. A flame is a very reactive environment where different kinds of nanostructure have been already synthesized. We have a shell particle, nanotube, and graphene. However, the carbon solids that are formed in highest amount are carbon nanoparticles. Why? Because in fuel-rich condition, we have that fuel fragments and low molecular weight hydrocarbon undergo two reaction of dehydrogenation and molecular mass growth to form a cluster of PIH and high molecular weight hydrocarbon that finally end up in the formation of single particle air carbon aggregates. Carbon aggregates are also the constituents of the cheapest and largest produced carbon nanomaterial in the world, carbon black. What is the difference between soot and carbon black? I found the answer to this question in a very recent publication on the carbon, when it is written, carbon black material are formed under the rigorously controlled thermal decomposition of carbon-rich feeds in inert or oxygen-depleted atmosphere. Carbon black production process is fundamentally different from that of black carbon and soot, both resulting from the incomplete, non-purposely engineered combustion of carbon sources such as fossil fuel, biofuel, and biomass. So I realized that I have been synthesizing carbon black since the beginning of my PhD. However, anyway, jokes apart, I really think that there is a need to change our perspective, and a flame becomes an engineered combustion, an incomplete combustion becomes a controlled thermal decomposition, and soot is no longer a byproduct, but it becomes a nanomaterial. So, in my opinion, sustainable fuel, flame synthesis, and unconventional particulate emission are the new challenges for the soot community. So we have still to roll our ball of soot on the hill like Sisyphus. And however, to meet these new challenges, we have to study in detail the relationship between the combustion condition and specific soot properties, such as chemical composition and nanostructure, because it is of fundamental importance to control their emission, but also to manage their synthesis. A general description of soot nanostructure and composition is already obviously known. Soot particles are composed by mixture of ordered and disordered parts, and with an H2C atomic ratio going from 0.5 to 0, and the presence of some other kind of heteroatoms according with the fuel sources. The other part is an assembly of basic structural units composed by few aromatic layers that, although nearly parallel to each other, are randomly stacked in the so-called turbostratic structure that was pioneering described by Oberlein in their pioneering work based on X-ray diffraction of aromatic disordered material. HRTM is a very powerful diagnostic technique to see the ordered part of soot, or whether it completely misses information on the disordered part, on the amorphous carbon, on the sp3 carbon bonds, on the hydrogen content, oxygen content. So there is the need to combine other kind of diagnostic to have an overall picture of soot structure. Three of the most important parameters for the characterization of carbonaceous material are reported here in the ternary phase diagram of amorphous carbon of Robertson. And they are the sp3 carbon content, the sp2 carbon content, and hydrogen content. However, a fourth important parameter is the ordering and clustering of the sp2 sites, and this is especially important for disordered aromatic carbon. However, where is soot on this diagram? To find the coordinates to draw the soot area, we have mainly used spectroscopic tools. And our experimental approach is to collect carbon particulate matter inside the flame with the isokinetic probe, or at the exhaust of engine systems with a sampling line that usually is composed by ice cooled trap to condensate the condensed species, and also a filter to collect soot particles. We have also used another kind of sampling method that consists in insection directly into the flame of a quartz plate to a massive collection of particulate matter inside the flame. And whichever the sampling mode, carbon particulate matter has been extracted with the chloromethane to separate soot from the organic fraction. And on these two main fractions, we have applied our spectroscopic study. So the first spectroscopic diagnostic that I'm going to describe is the Raman spectroscopy. The Raman spectrum of whichever carbonaceous material, disordered carbonaceous material, is characterized by these two main peaks. The D peak is due to where D stands for disordered, is due to the breathing of aromatic rings, and it is forbidden in perfect graphite, and it becomes active in the presence of disorder. The other peak, the G peak, where G stands for graphite, and this is due to the in-plane bond stretching of all pair of carbon sp2 atoms. Does not require the presence of aromatic rings. Raman spectroscopy has been historically used for the characterization of perfect carbon allotropes like graphite, nanotubes, and only in 1999 we have the publication of the first paper on soot characterization by Raman spectroscopy by Dippel et al. But it's only after the spread of Raman spectroscopy as diagnostic tool for graphene that it became a popular diagnostic also for the soot community. And the most investigated parameter derived from Raman spectroscopy is the ID to IG ratio, namely the intensity, the ratio between the intensity of the D peak and the intensity of the G peak. This is particularly useful because it is possible to derive the aromatic layer length, this parameter. However, the relationship between the ID to IG ratio and the LA is not monotonic, and we can distinguish two different kinds of relationship. The first one is known as the twin scanning relationship, and it is valid for LA higher than 2 nanometer. And in this correlation, the area of the cluster, aromatic cluster, is inversely proportional to the ID to IG ratio. For LA lower than 2 nanometer, we have that another kind of correlation where the area of the aromatic cluster is proportional to the ID to IG ratio. So this formula was proposed by Ferrari and Robertson, and it implies that if there is a development of the D peak, we have an increasing order. Being soot usually characterized by an LA lower than 2 nanometer, we have that the correct formula to apply is that proposed by Ferrari and Robertson. However, this is a tricky aspect of soot characterization by Raman spectroscopy, because being twin scanning formula more famous, often it is applied also to soot, leading to incorrect result. To calculate the ID to IG ratio, it is necessary to deconvolve the spectrum, and also this is a tricky aspect of the Raman spectroscopy for soot, because there are a lot of different kind of deconvolution method proposed in literature. However, we have performed a very detailed analysis at different excitation wavelengths of the spectrum of Raman spectrum of soot, and we have found that the best fit is obtained with the 5-band methods, where composed by a G band for the braid-Wigner funnel, with a braid-Wigner funnel for the G peak, 3 Lorentzian curves for the D5 and D4 peaks, and a Gaussian curve for the D3 peak. With this deconvolution method, we have derived the LA from Raman and compared these values with those obtained by HRTM, finding a very good agreements. Well, not only the ID to IG peak is useful, but also other important information can be derived from Raman spectroscopy, as for example, the olefinic carbon contribution. Let me explain what is reported in this diagram. 1,600 centimeter minus 1 represent the band limits of G peak for purely aromatic carbon. However, the G peak can upshift to higher value if there is the presence of olefinic carbon, because they are characterized by a shorter bond length that imply a higher vibration frequency. Also, the D5 is related to the olefinic carbon, because it is due to transpolylacetylene segments lying the grain boundary. So the ratio between the intensity of D5 peak and the intensity of D peak is in a certain way a relative abundance between the olefinic carbon and the aromatic carbon. So its increase, indeed its increase, where, as you can see in the diagram, where correlates with the upshift of the G peak position. So it's possible to derive olefinic carbon contribution from these two parameters. And also information can be derived from the width of the peak. It has been found that as soot age, so as the ID to IG ratio increases, so LA increases, we have a broadening of the peak of the G and D peaks. We have attributed the increase of the D peak width to the broadening of the aromatic cluster size distribution. whereas the increase of the G peak indicates that we have the broadening of the sp2 bond configuration. So as the aromatic layer lengths increase within the particle diameter, we have also the rising or layer distortion and the phenomena of puckering and warpening occur. From Raman spectroscopy, it is also possible to derive the hydrogen content of carbonaceous material. It was reported by Casiraghi et al. That as the hydrogen content increase, the slope of the fluorescent background of the Raman spectra increase as well. They found this empirical correlation that correlate the hydrogen content with the ratio between the slope of the fluorescent background and the intensity of the G peak. This empirical correlation is valid for for carbon with an hydrogen content higher than 20%. We have performed the spectroscopic analysis of different kinds of carbon. We have derived the ratio between the fluorescence background and intensity of the G peak, and we have also calculated with other kind of techniques the amount of molecular hydrogen, and we have found that effectively the Casiraghi equation well fit our data. However, we have extended our experimental analysis also to carbon with a lower hydrogen content, find a new correlation that is valid also for hydrogen pure carbon. So, summing up, with Raman spectroscopy, we can obtain quantitative information on the aromatic layer extension and on the hydrogen content, but also qualitative information on the sp2 olefinic contribution and on the different kind of nanostructural disorder. Another valuable spectroscopic technique for analyze soot composition is Fourier transform infrared spectroscopy, FTIR, because it is able to identify functional group and bonding as aliphatic and aromatic hydrogen and oxygen containing functionalities. So it allows to draw in some way the age of an aromatic system featuring soot as done by Akhter and Chung-Ai in their pioneering work on hexane soot. Here in this slide, I highlighted the absorption region where it's possible to obtain information on the different kind of CH bond. At high wave number, we have the occurrence of the CH stretching of aromatic and aliphatic hydrogen, whereas at low wave number, we have the occurrence of the aromatic autoplane bending, CH autoplane bending region. We have developed a method for the quantification of hydrogen content in carbonaceous material. To do this, it's fundamental to perform a detailed analysis of the different CH vibrational modes of aliphatic and aromatic standard and to derive calibration factor for these modes. We have also deconvoluted the CH stretching region and the CH bending region of carbonaceous material and to derive in their single components and multiply each of them for the appropriate calibration factor. Doing this, it is possible to quantify the aliphatic and aromatic hydrogen, but it's possible also to derive the sp3 and sp2 protonated carbon. If we can consider the sp3 carbon all protonated and the non-protonated one negligible, we can also derive the total sp2 carbon content. With this method, we have also studied the dehydrogenation process of soot along two flame, a methane flame and an ethylene flame. We have found that for aromatic hydrogen, there is a rapid consumption of this kind of hydrogen along the flame, and the final value are very similar in both flames. A different behavior has been found for aliphatic hydrogen Indeed, there is a slower and lower consumption of aliphatic hydrogen in the methane flame and the complete consumption of aliphatic hydrogen in the ethylene flame. We have looked at the bond dissociation entropy of the different kind of CH bonds, and we have found that aliphatic hydrogen are characterized by the lowest bond dissociation entropy. So why does aliphatic hydrogen survive in the methane flame? We have schematized the process of the hydrogenation and mass growth on soot, looking at the species involved in the phenomena. And we have that the H radical acts as abstracting agent, molecular hydrogen acts as the activating agent, and the CH bond on the solid, on the surface of the soot particle acts as active sites. The phenomena is described by this kinetic reaction, and the overall process is dependent on the temperature, that are rather similar in both flame, and the ratio between the H radical, the concentration of the H radicals, and the molecular hydrogen. So the reason why the hydrogenation process is slow in the methane flame is due to very high molecular hydrogen content that prevents soot for further hydrogenation. Finally, with the FTIR spectroscopy, we have tried to obtain information on the oxygen content of soot derived from oxygenated fuel. In this slide, we have analyzed soot coming from an ethylene flame, and from the same flame with a part of the ethylene was substituted with the dimethyl furan. And we have measured the mass absorption coefficient of both samples, and here is reported the difference between these spectra. And we have found that there are clearly peaks that indicate a higher concentration of carbon double bonded and single bonded with oxygen, and in the dimethyl furan soot. And also we have found a reduction on the aromatic hydrogen content. So on the basis of this reduction aromatic hydrogen, we have calculated the surplus of oxygen that featured dimethyl furan soot. And this is around 2.5 to 5 weight%. So with FTIR spectroscopy, we can derive the hydrogen content, but also the sp3 and sp2 carbon content, and we can have qualitative information on the different kind of oxygenator functionalities. The last method, the last spectroscopy that I'm going to describe is UV visible spectroscopy. The UV visible absorption of carbon materials is due to pi-pi electronic transition. And the localization of the pi electrons on the sp2 cluster introduces a sort of medium range order that determines the electronic property, but also the value of specific optical parameters as the mass absorption coefficient, the dispersion coefficient, and the optical band gap. These three values, these three parameters, have been historically used in the for the study of soot formation since the 1961, where Millikan reports this very nice correlation between the H2C ratio of soot and its dispersion coefficient to the work of Wersborg and J. Coward that derived the heavy hydrocarbon and soot volume concentration from the absorption data using the mass absorption coefficient, and to the paper of Patrizia Minutolo and Nini D'Alessio that first introduced the concept of optical band gap in the soot community. The optical band gap can be derived exporting the absorption spectra in the tau domain, and it can be calculated as intercept to the energy axis of the straight line fitting the spectrum. It has been found that as the optical band gap decreases, there is an increase of the aromatic cluster size. We have derived a method to, developed a method to derive the from the carbon particulate matter spectrum, the spectrum of soot and organic carbon. Can be schematized in the 4 steps, and in the first step we have to plot in the Tauk diagram the data obtained for wavelengths above 685 nanometer, because in this spectral region we consider that only soot absorbs. So we can derive the band gap, and so from the Tauk formula derive also the absorption spectrum of soot. The spectrum related to organic carbon can be derived as difference between that of particular matter and that of soot, and to the spectrum of organic carbon can be applied the Tauk method as well. In this way, we can decompose the carbon particular matter spectrum into its components due to soot and organic carbon. And to this single spectrum, we can, from this single spectrum, we can calculate the dispersion coefficient as reported in this diagram. Also from the band gap evaluated, we can obtain structural information applying the method developed by Robertson and Aurélie. And so we can derive the aromatic layer lengths for soot that show a increasing trend along the flame, and the number of rings for the organic carbon that indeed has a nearly constant value of about 10-12 rings for molecules. We have also this paper was this method was developed in collaboration with Professor Bengtsson on the University of Lund, and it was found to be able to be applied, successfully applied to in situ, but also to ex situ measurement. We have also performed a size-resolved analysis of the optical properties of soot and coupling size-exclusion chromatography with the visible detector. SEC is able to physically separate soot into its molecular weight segregated fraction that usually are 3. We have the molecular weight, the peak due to residual organic carbon, the peak due to single particle, and the peaks due to carbon aggregates. From the spectra of this molecular weight segregated fraction, we have calculated the optical band gap that was found to be around 1.5 and 1.2 for residual organic carbon and single particle respectively. However, we have found a decreasing trend of the optical band gap evaluated for carbon aggregates along the flame, going from 0.5 to nearly 0 electron volt. This decrease does not correspond to an increase of the aromatic layer extension. So to justify this result, we have thinking about the possibility of intraparticle, interparticle electronic tunneling effect between the particle, but also to the interaction among the pi system in carbon material with a very high density of sp2 cluster, and also to the effect that the curvature, ring arrangement, and radicals may have on the band gap value. So from revisible spectroscopy, we can derive quantitative information on the aromatic layer extension, but also quantitative parameter as the mass absorber coefficient and dispersion coefficient. So now we have the coordinates to draw the soot and organic carbon area on the ternary phase diagram. The last slide. In the last slide, I'm going to describe the last results obtained with implementation of the methods described, and also to meet the challenge that I have listed in the introduction. We have analyzed soot from sustainable fuel, in particular we have analyzed the effect of oxymethyl ethers, OME 2, 3, and 4 on soot chemical feature. We have collected the soot from an ethylene flame, and the same flame where part of the ethylene was substituted with the different kind of oxymethyl ethers, and we have found that soot from the different OME are characterized by lower aromaticity that was specified by the lower ID2IG ratio and the lower mass absorption coefficient. However, FTIR spectroscopy has highlighted the higher presence of carbon double bonded with oxygen in the OME soot. We have also analyzed the carbon particulate matter emitted from an hydrogen fuel engine, and we have found that in all the conditions, in terms of different speed and loads, we have the formation of PIH nanoparticle. However, only at higher temperature, namely at higher engine speed, we have the formation of carbon aggregates. All these pollutants are due to the lubricating oil that passes into the combustion chamber and starts its thermal degradation. We have also analyzed particulate emission from brakes. We have to underline that carbon represented just the 10% of the sample. However, we have seen that soot, the insoluble carbon fraction, is characterized by inevident aromatic character, probably due to oxidation reaction that occur at the interface of the brake. And the organic carbon, indeed, on the other side, the organic carbon is characterized by PIH and nanoparticles. We have also oxidized soot. We have performed the mild oxidation of soot at 450 Celsius degree for 1 hour, and we have analyzed soot before and after this mild oxidation. We have found that after the treatment, soot becomes water soluble, that the surface area increases 5-fold, and the sample was amorphous carbon free. It has been the samples have been analyzed by Raman spectroscopy and infrared spectroscopy, and we have found that soot after the partial oxidation is characterized by a strong increase of the oxygen content, a low mass absorption coefficient in the infrared range, and also a higher hydrogen to a higher ID to IG ratio. To justify this contrasting result, we have to remind that during the oxidation process, amorphous carbon is the first to burn, so only the most graphitic carbon remain, justifying the high ID to IG ratio. However, the low mass absorption coefficient is due to the fact that part of carbon has been substituted by oxygen, lowering the absorption behavior of our sample. And this is the last result. We have synthesized in flame carbon quantum dots. Carbon particulate matter was collected by thermophoretic sampling in different flame, where we have changed the CO, the carbon to oxygen feed ratio, the residence time, and also the fuel nature, going from ethylene to benzene. And we are able to synthesize different kind of carbon quantum dots with different emission in the blue, green, and yellow region, and with different kind of quantum yields going from 2 to 25%. So this is my last slide. I hope that I have effectively explain that methods based on spectroscopy diagnostic represent very valuable tools to study soot, looking at this as a friend as a source of industrially relevant carbon materials, but also as a foe, as a source of air pollution, climate change, and adverse effect on human health. This intriguing double vision of soot was already captured by Faraday in 1861. When he wrote, you would hardly think that all these substances which fly about London in the forms of soot and blacks are the very beauty of the flame. So let me acknowledge my colleagues at the Siena Laboratory in Naples, Barbara, Maria Maddalena, Fernando, and Antonio. And also I would like to thank Mariano Sirignano from the University of Napoli. And let me I'm also particularly grateful to Anna Sciaiolo. I had the opportunity to grow scientifically under her guidance, and she is a continuous source of inspiration and very precious suggestions. So thank you very much for your attention.
Thank you. Very nice presentation. Thank you, Lina. Okay, so I will, we have time for questions, of course. I don't know if there is already someone with the question in the audience. Salvatore.
Yeah, I have I have a question. Yeah, thank you, Lina, for this nice presentation. I wonder, since you have talked about basically ex situ diagnostic tools, right? So I was wondering, what are you planning to, or have you ever analyzed in situ measurements, and what additional knowledge regarding soot structure, soot formation, this type of measurements can bring to the community?
Regarding soot, I think that the analysis of online in situ ex situ analysis is quite similar, because usually what we can lost with an ex situ analysis is the most light part of the carbon particulate matter. So we have a long tradition also online spectroscopic diagnostic, like extinction and so on. So we always perform also in situ characterization to check that everything is okay, that we are not perturbing the system, that we are not create artifacts during our analysis. So however, a deep analysis as I have shown, is possible only with this combination of diagnostic that usually are performed by ex situ measurements. So we have also to be care with this because the tricky point is not the analysis, the tricky point is the sampling. However, we have a long tradition and we on the sampling of the condensed physics and the particulate matter in the flame. So we are rather confident that we are doing well.
Okay, and you show that all these, techniques will be complementary to each other. No one can exclude the other. Yeah,
it's not enough. Yeah, to have a picture, because the object is quite complicated. I mean, it's a tuberstatic structure, a lot of different kind of carbon, hydrogen, oxygen. So it's not easy as let me say, as a carbon allotropes that is a very well-defined structure. So to control everything, you have to obtain information, and also to match information from different kind of techniques.
I have another small curiosity, if I may, a little question. How much of this, how much of user guidance, user knowledge, prior knowledge is required to analyze all these results from the spectrometer, from Raman, FTIR, and all this kind of stuff? And how much, in your opinion, can be automated by we are in an era that all the human knowledge can be kind of replaced by automatic feature selection, feature extraction. How this can be, what is your opinion about the applicability of these techniques to
when you have to deal with the deconvolution, you have always to be check of what are you doing. No kind of deconvolution can be applied a priori, because you have always to look at your spectra and so for FTIR, for Raman spectroscopy, it is impossible. We have for visible spectroscopy it's different, because if you want to measure the mass absorption coefficient, is something that more simple, because you have your spectrum and you can derive the dispersion coefficient also automatically. But when you have to deal with the convolution, I think that it is impossible. This is a critical aspect of the analysis of this kind of in the analysis of this kind of spectrum, because usually it can sometimes people apply a priori methods where it is not possible, because you have always to look at what you are analyzing. So it depends from the spectroscopy.
Okay, thank you, and thank you again for the nice talk.
Thank you.
Thank you very much, Mustafa. I see that you have your hand raised. Mustafa?
Mustafa. Please, Mustafa.
We cannot hear you, Mustafa. You can write
maybe I start
in the
with
chat
question,
if you
while Mustafa figures out the audio problem. So where are we when it comes to models and in comparison to these to experimental data? Are we already at the phase where models are predictive, or we are not yet there?
I think that the most tricky point in the modeling of soot formation and nanostructure is to catch the dehydrogenation process, because we can reach very low hydrogen content, where it does not correspond to a large increase of the aromatic layer. So it is not easy to predict the dehydrogenation process, however sometimes happens. So I think this is the tricky aspect, also because a model can model the size, the number, and I think the each relation of the soot particle. They cannot give more details than this.
Thanks. I don't know if Mustafa solved these issues. No. Then in that case, I would like to thank Lina again for a very nice presentation, for the availability, and I give all the the appointment to the next talk, which I don't know when will be.
In 2 weeks. The 7th of July. And I also would like to remind everyone that this lecture, as well as all the previous ones, will be available on our YouTube channel, the Belgian section of the Combustion Institute, the YouTube channel, and there you can comment. And if you have, if you rewatch the lecture, you have any other question, have any question to ask, you feel free to contact our speaker.
But always, it's mostly interesting to participate in the live session.
That's true. That's true. So, so yeah, see you in 2 weeks' time then. Thank you, Lina, for your talk and for accepting our invitation.
Thank you for the invitation, and thank you very much.
Bye-bye.
Bye-bye.
Have a nice weekend,
Bye,
everyone. Bye-bye.